Dear students, in last class we have learned DIT FFT algorithm, and at the end we got an expression for DFT point x of k as f1 of k plus wn raised to k plus f2 of k, where k is equal to 0, 1, 2 and so on up to capital N minus 1. If we have to calculate 8-point DFT, that is n equal to 8, we need to calculate n by 2 equal to 4-point DFTs for even indexed samples and odd indexed samples as f1 of k and f2 of k, and then combine them to get x of k. That is x of 0 equal to, we have to put now in place of k 0, f1 of 0 plus w8 raised to 0 into f2 of 0. w8 raised to 0 is 1. So we get x of 0 as f1 of 0 plus f2 of 0. Next we have to calculate x of 1 by putting k equal to 1 in this x of k expression. So we get f1 of 1 plus w8 raised to 1 into f2 of 1. w8 raised to 1 value is 0.707 minus j 0.707. Therefore, x of 1 will become f1 of 1 plus 0.707 minus j 0.707 into f2 of 1. X of 2 is f1 of 2 plus w8 raised to 2 f2 of 2. w8 raised to 2 is minus j. So we get f1 of 2 plus minus j into f2 of 2. X of 3 equal to f1 of 3 plus w8 raised to 3 into f2 of 3. But w8 raised to 3 is minus 0.707 minus j 0.707. Therefore, x of 3 can be written as f1 of 3 plus bracket minus 0.707 minus j 0.707 into f2 of 3. We have to calculate x of k for k equal to 0 to n minus 1, but we are having n by 2 point DFTs of even indexed and odd indexed samples of previous stage, and also f1 of k and f2 of k are periodic with a period of capital N by 2. This we can say by property of periodicity of DFT. What we can say, f1 of k and f2 of k are periodic with periodicity of capital N by 2. Writing that f1 of k plus capital N by 2 is equal to f1 of k, and f2 of k plus capital N by 2 is equal to f2 of k. This is by periodicity property of DFT. So here I have written in bracket f1 of k and f2 of k are N by 2 point DFTs with a period of capital N by 2. For calculating x of 4, x of 5, x of 6 and x of 7, we will write f1 of 4 as f1 of 0 plus 4. To calculate x of 4, x of 5, x of 6, x of 7, we will write by property of periodicity f1 of 0 as f1 of 0 plus 4. f1 of 0 plus 4 will be equal to f1 of 0 only. It is by property of periodicity. Similarly, f2 of 0 plus 4 will be equal to, similarly, f2 of 0 plus 4 will be equal to f2 of 0. You can write f1 of 5 as f1 of 1 plus 4 equal to f1 of 1 only, and f2 of 1 plus 4 by periodicity properties f2 of 1. Similarly, we can write f1 of 2 plus 4 as f1 of 2, f2 of 2 plus 4 as f2 of 2, f1 of 3 plus 4 as f1 of 3, f2 of 3 plus 4 as f2 of 3. This is because of periodicity property. Then can I write for x of 4? I can write for x of 4, x of 5, x of 6 and x of 7 this way. Now x of 4, it is in continuation with x of 0, x of 1, x of 2, x of 3. Next x of 4 equal to f1 of 4. But what is f1 of 4? We have written here f1 of 0 plus 4. That means f1 of 4 is equal to f1 of 0. Similarly, f2 of 0 plus 4, that is f2 of 4 is equal to f2 of 0. We will substitute that value here. f1 of 4 will become f1 of 0. Here f2 of 4 will become f2 of 0. So x of 4 is equal to f1 of 0 plus w8 raised to k. K is what? K is 4. That means I can write it as 4 plus 0. W8 raised to 4 w8 raised to 4 is minus 1. Therefore, this expression can be written as f1 of 0 minus f2 of 0. X of 5 equal to f1 of 1 plus w8 raised to 4 plus 1, because we have seen f1 of 5 may be written as 1 plus 4. f1 of 5 may be written as f1 of 1 plus 4, and f1 of 1 plus 4 because of periodicity properties f1 of 1, and similarly here f2 of 1 plus 4 is f2 of 1. Here we will have to make use of law of exponent, that is a raised to m plus n is equal to a raised to m into a raised to n. When we do that, w8 raised to 4 will become minus 1 into w8 raised to 1 will become 0.707 minus j 0.707. Similarly, by making use of periodicity property, x of 6 can be written as f1 of 2 minus j into f2 of 2. And x of 7 can be written as f1 of 3 minus bracket minus 0.707 minus j 0.707 bracket complete into f2 of 3. So like this we can compute 8-point DFTs using 4-point DFTs. And these computations of DFTs using FFT algorithm we will show as butterfly diagram. Butterfly diagram is nothing but actually signal flow graph, but the shape of that signal flow graph appears as butterfly. It is named so. Now here I have shown f1 of k and f2 of k. These are 4-point DFTs. And these are also 4-point DFTs. We have to obtain from these 4-point DFTs 8-point DFTs, that is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. We have seen how to write for x of 0. X of 0 is f1 of 0 plus f2 of 0. We have written that in previous page. If you want, you can see. X of 0 equal to f1 of 0 plus f2 of 0. This is summation point. Here I am adding f2 of 0 to f1 of 0. So I am going to get here x of 0. So here and here I will show 1 and 1. Next we have to calculate x of 1. X of 1 is equal to f1 of 1 plus bracket 0.707 minus j 0.707 f2 of 1. That means I have to multiply f2 of 1 with 0.707 minus j 0.707 and then add it to f1 of 1. And that is nothing but the value of w8 raised to 1. So f2 of 1 into w8 raised to 1 is to be added to f1 of 1. Next we have to calculate x of 2. X of 2 is equal to f1 of 2 plus w8 raised to 2 f2 of 2. On simplification we get f1 of 2 plus bracket minus j into f2 of 2. So in place of minus j I will write in butterfly diagram w8 raised to 2 only, because it takes less space there to write. f1 of 2 is here. To this I have to add w8 raised to 2 into f2 of 2. Next we have to calculate x of 3. X of 3 is equal to f1 of 3 plus bracket minus 0.707 minus j 0.707 into f2 of 3. But this bracket here of complex number is w8 raised to 3. That we will write in butterfly diagram. So f2 of 3 into w8 raised to 3 plus f1 of 3. That will write here. Next we have to calculate x of 4. X of 4 is f1 of 0 minus w8 raised to 0 into f2 of 0. f2 of 0 into w8 raised to 0 we get at this point, but we need minus f2 of 0 into w8 raised to 0. Therefore I will write here minus 1. Remember, 1 is nothing but w8 raised to 0. So to subtract f2 of 0 into w8 raised to 0 from f1 of 0, you bring f1 of 0 here. f2 of 1 is f1 of 1 minus, so I have to write here minus 1, w8 raised to 1 into f2 of 1. x of 6 equal to f2 of 2 minus w8 raised to 2 into f2 of 2. X of 7 is equal to f1 of 3 minus w8 raised to 3 into f2 of 3. So what we are having here? We are having here f1 of 0 plus f2 of 0. Here we are having f1 of 1 plus 0.707 minus j 0.707 f2 of 1. X of 2 is equal to f1 of 2 minus j f2 of 2. X of 3 equal to f1 of 3 minus f1 of 3 plus x of 3 equal to f1 of 3 plus minus 0.707 minus j 0.707 f2 of 3. X of 4 equal to f1 of 0 minus f2 of 0. X of 5 equal to f1 of 1 minus 0.707 minus j 0.707 f2 of 1. X of 6 equal to f1 of 2 minus of minus j, that will become plus j f2 of 2. X of 7 equal to f1 of 3 minus 0.707 minus j 0.707 f2 of 3. In the same way, we can combine 2-point DFTs to obtain 4-point DFTs, and we can combine the given inputs after decimation in time and after reversing their bit order, we can get 2-point DFTs. Example: An 8-point sequence is given by x of n equal to two comma 1 comma 2 comma 1 comma 1 comma 2 comma 1 comma 2. Compute eight-point DFT of x of n by radix 2 decimation in time FFT. Also sketch the magnitude and phase spectrum solution. Eight-point DFT by radix 2 DIT FFT. First we have to reverse the order of bits of x of n the given sequence is to be arranged in the bit reversed order. x of n in normal order x of n in bit reversed order x of 0 equal to 2, x of 1 equal to 1, x of 2 equal to 2, x of 3 equal to 1, x of 4 equal to 1, x of 5 equal to 2, x of 6 equal to 1, x of 7 equal to 2. X of 0 equal to 2, x of 4 equal to 1, x of 2 equal to 2, x of 6 equal to 1, x of 1 equal to 1, x of 5 equal to 2, x of 3 equal to 1, x of 7 equal to 2. I have explained how to write x of n in bit reversed order in last class. Now these x of n samples in bit reversed order I will use to compute 2-point DFTs. Then using 2-point DFTs I will calculate 4-point DFTs, and using 4-point DFTs I will calculate 8-point DFTs. In solving this problem, you will learn how to obtain 2-point DFT by using x of n in reversed bit order, and how to obtain 4-point DFTs using 2-point DFTs. Finally, you will learn how to obtain 8-point DFTs using 4-point DFTs. First, I will draw the butterfly diagram in reverse order. Making use of the butterfly diagram which I have explained before taking up this example. Now you can see here 8 parallel lines drawn to compute 8-point DFT using DIT FFT algorithm. Using these 8 parallel lines, we will complete the required butterfly diagram. And in this figure, to the left side, we have given the bit order reversed inputs, that is x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, x of 7. And on the right side, we have written DFT points, capital X of 0 to capital X of 7. Now I have reproduced here the butterfly diagram that is used to compute 8-point DFTs by combining the 4-point DFTs, which I discussed before taking up this example. Now, before this 8-point DFT computation, by combining 4-point DFTs, we will be having computation of 4-point DFTs by combining the 2-point DFTs. So next I will show you here how the butterfly diagram appears for it. Now you can see here. First butterfly diagram for 4-point DFT computation and second butterfly diagram for 4-point DFT computation. The output lines here are carrying 4-point DFTs to the butterfly diagram used for computation of 8-point DFTs as inputs. So you can see here I have written 4-point DFTs. That means on these lines we are having 4-point DFTs. And the parallel lines here, which are coming out of butterfly diagram used to combine 4-point DFTs to get 8-point DFTs. We have 8-point DFT as output. And for computation of 4-point DFTs, inputs are 2-point DFTs. The 2-point DFTs are obtained by combining the bit reversed input samples, which are shown here. Now I will show you the butterfly diagram used for computation of 2-point DFTs. Now you can see here the butterfly diagram used for computation of 2-point DFTs using the bit order reversed input samples that I have written here. Bit order reversed decimated inputs and here 2-point DFTs. This complete diagram is the butterfly diagram used for computation of 8-point DFTs using the DIT FFT algorithm, in which we are making use of bit order reversed decimated inputs. Now I will write here the input values as x of 0, x of 4, x of 2 and so on up to x of 7. and show you how to make the computations, right? Now you can see the input sample values which we wrote in table before coming to this stage. And also you can observe here W2 raised to 0, W2 raised to 0, W2 raised to 0 and W2 raised to 0 for 2-point computation of DFT. Here input is 1, W2 raised to 0 is 1. 1 into 1 is 1. Here this line will carry 1. 1 plus 2 into 1, 2. So we get here 2 plus 1, 3. Here 1 into minus 1, minus 1. 2 minus 1 is 1. Similarly, Similarly, 2 into 1, 2 at this point. That 2 will be carried by this arrow mark. 1 into 1 is 1. 1 into minus 1 is minus 1. So 2 minus 1 will get 1 here. And here 2 plus 1, 3. One plus 2, 3. 1 minus 2, we get minus 1 here. 1 plus 2, we get 3. 1 minus 2 is minus 1. So now here we have obtained 2-point DFT values. These values we have to multiply with the gains on their lines and give as input to the next stage, that is used for combining the 2-point DFTs to obtain 4-point DFTs. So these are arrow marks here downward. W4 raised to 0 is 1. W4 raised to 1 is minus j. This is minus j here, and this is also minus j. W4 raised to 0, 1. W4 raised to 0 is 1. Now we will combine the 2-point DFTs obtained to get 4-point DFTs. Three into 1, 3. 3 plus 3 into 1, 3. I am going to get here 6. Next 4-point DFT. 1 into minus j plus 1 into 1, 1. So 1 minus 1j. Next 3 into 1, 3. 3 into 1 3 minus 1, that means minus 3, that will become equal to 0. One into 1 1, 1 into minus j into minus 1 plus j, so it will be 1 plus 1j. Next 3 into 1 3, 3 into 1 3, 3 plus 3 6, minus 1 into 1 minus 1, minus 1 into minus j plus j, so minus 1 plus j. Next 3 into 1 3, 3 into 1 3 minus 1, this will become 0. Next minus 1 into 1 minus 1, minus 1 into minus j plus j into minus 1 minus j, so minus 1 minus j we get. Next we have to combine these 4-point DFTs to obtain 8-point DFTs according to this butterfly diagram or signal flow graph. But before that, we must know the values of W8 raised to 0 equal to 1, W8 raised to 1 I will write those values here. You will have to make use of calculator to compute the products, then addition and subtraction. .707 minus j 0.707, then W8 raised to 2 equal to minus j W8 raised to 3 equal to minus 0.707 minus j 0.707. Since I don't have space here to write, I have written these values here. Next 6 into 1 6, 6 into 1 6, 6 plus 6 you will get here 12, so I will write here 12. Next, to compute capital X of 1, will make use of calculator. Minus 1 plus j, you make use of brackets, bracket complete, into W8 raised to 1. W8 raised to 1 is 0.707 minus 0.707 I plus 1 minus 1j into 1, that means 1 minus 1j. 1 plus 0.414 j you will get. So right here 1 plus 0.414 j. Next we will compute x of 2. X of 2 is 0 into 1 0 plus 0 into w8 raised to 2, that will be 0 only. So 0 plus 0 is equal to 0. Next we have to compute x of 3. 1 plus 1j into 1, that is 1 plus 1j only. Bracket 1 plus 1I plus minus 1 minus j into w8 raised to 3. w8 raised to 3 is minus 0.707 minus 0.707 I equal to 1 shift equal to, you get imaginary part as 2.414 j. One plus 2.414 j. Next we have to calculate x of 4. X of 4 is 6 into 1 6. 6 into minus 1 minus 6, that will be equal to 0. Next we have to calculate x of 5. X of 5 is 1 minus 1j into 1 minus 1 plus j into w8 raised to 1. So make use of calculator. One minus 2.414 I. That is j for us. Similarly, we will calculate x of 6. X of 6 is 0 into 1 0, 0 into w8 square into minus 1 is 0. So 0 minus 0 will be 0. Next we have to calculate x of 7. X of 7 is equal to 1 plus 1j into 1 minus 1 minus j into w8 raised to 3. Use your calculator. One plus 1 j minus bracket minus 1 minus 1 I into minus 0.707 minus 0.707 I bracket complete equal to 1 shift equal to minus 0.414 I. So 1 minus 0.414 J. I and J both are equal to under root minus 1. So I can use I in place of J or J in place of I. So now we will write 8-point DFTs in one line on next page. Eight-point DFT of x of n equal to 12 1 plus 0.414 J 0 1 plus 2.414 J 0 1 minus 2.414 J then 0 1 minus 0.414 J. With this we have completed the solution of one example on computation of 8-point DFT using DIT FFT. Dear students, in next class I will be taking up computation of IDFT, that is inverse discrete Fourier transform computation using DIT FFT algorithm. I'll stop here. Thank you.